Hi everyone, today I'm going to show how to use Andrej Karpathy's Micrograd. It's artificial intelligence at its most fundamental level. Andrej Karpathy, he works at OpenAI that makes ChatGPT. So let's begin. Okay, I'll start up here. So import NumPy and matplotlib for plotting a graph. NumPy is for calculating stuff easy. Then create a function here. This 3 goes in here, and you do 3 squared, which is 9. Then 3 times 9 is 27. Here, I'll write it down real quick. So 27. Now you have 4 times this 3, which is 12. So I'll write that down, 12. Whoops. Now you have 27 minus 12, which is 15, plus 5 is 20. So that's where that 20 comes from. So what I'll do is go down here next, and this will create numbers from -5 to 5 in steps of 0.25. So it's -5, and then you add 0.25 to that, which is 4.75, until it gets to that. So that's what the x's are, and it passes each of those into this function. Okay, so now I'll uncomment and plot it on a graph. So as you can see, it looks like a parabola. So now go down here, and what this does is it shows where the slope is 0, which happens to be right here, and it was previously calculated to be 2/3. The x is 2/3 right about here, and so that's where the slope is 0. Like if I connected a straight line from here to here, that would be flat. But if I connected it from here to here, it would be tilted upwards, so it would have a big slope, or in other words, a big gradient. So that's what this is doing. And if you remember from calculus, you have f of x plus h minus f of x divided by h, which this is basically from a a straight line graph. You have y2, which is this, minus y1 over x2 minus x1. But in this case, you would have x plus h minus x. This would be x2, and this would be x1. So you have x2 minus x1. But to simplify it, you have x minus x, and so they cancel out, and that's where the h comes from. Okay, so if I run it, it shows this. So this is the numerical derivative, and because of the computer's floating point precision, it can only go to a certain amount of decimal points. That's why it rounded it off to this. This basically means move the decimal point over 6 places and fill in the gaps with zeros and put a 0 on the left of the decimal point. So it's a really small number. All right, now come down to here and say a is 2, b is -3, c is 10. So if we do a plus b, or sorry, a times b, that's -6, and add 10 to it, that's +4. So if I run it, so this outputs +4. Next, if we go down here, you can see that we have the 2, and the -3, and the 10. So what we can do to calculate the gradient is say this, the a times b plus c. You have a times b plus c, and just say d1 is equal to that. And now you add a tiny bit, this amount, for example, to c, and then that makes d2, because it redoes the calculation here. So what you then do is say whatever this, in the case of the regular straight line graph on an xy graph, the new number, or the y2, minus the old number, which is y1, over, and remember that's a simplified version of x2 minus x1. So what this is saying intuitively is whenever you barely bump up c, how many times that bump up amount does the new number change? So if I uncomment this, then it will say whatever the new number is minus the old number divided by the bump up of c. And if I run it, it shows approximately 1 is the answer. So why is that? It's because if I barely increase c right here, the total answer changes by 1 time that amount. So if I bump this up by 1, then I divide by 1, the amount it changed is 1. If I bump this up by 0.1, the increase is 0.1, and so if I divide by the 0.1, that comes out to be 1. So in addition, derivative is 1. So now, if I just run through this one really quick, if I barely bump up 2, or if I barely bump up a, then how much does it change? So I could bump up a by a tiny amount, and the amount that it'll change is by whatever b is. The reason is because I'm taking this 0.0001 and I'm bumping up b by that amount, I'm bumping up a by that amount, but that bumped up amount gets multiplied by b, which is -3. So the slope would be -3. So if I run it, and there's the slope, -3. Okay, then if I bump up b, do this super quick, it follows the same pattern, so the slope would be a, because it's multiplying that change by a. Okay, and there it is. And a is 2, so the slope is 2. Alright, now put it back to c real quick, and then move on from here. Okay, now this is creating what Andrej calls a value object. Well, it is a value object. Or it's creating a value class, which you can make an object from. So what this does is, first of all, this repr, what it's doing is it's displaying the data so that you can actually see what it says in human readable form. Because if you don't have this and you run it, watch. Okay, so if I put L and run it, it shows the memory location of that, and that's just run from the main file. Okay, so now I'm going to remove that. Whenever I actually run it with this not commented out, then it'll show stuff that's human readable, like actual numbers and stuff like that. Okay, so now what this does is it's taking in data, and this is just keeping track of the, when you go through the process of the calculations, it's keeping track of the previous things that depend on that. Like if you say C is A plus B, then this would contain A and B. And this op means what kind of operation is it doing, like multiplication, addition, etc. And this label is saying what is the label of it. Okay, so here it's making these in the self things, and so you should know about that part. If not, you can ask ChatGPT or just look it up on Google what the self part does. Okay, so now we know what that and that does. So now move to here where it says add. So it's taking the data and the other data. Well, what this is doing is that add, it's actually saying whenever I run stuff on this value object, see, this is A, this value object with 2 inside of it. This is -3, which is B. And so if I do A times B, what that's doing in the background, well, if I did A plus B or A times B, let's just do multiply real quick, because this and this are doing pretty much the same thing. So the multiply, what that's doing is saying whenever I take this value object and this value object, whenever it sees this multiply symbol, it's going to run this. And it's going to take in its self data, which is the, just say if I did A times B, it's saying A dot that of B. So that's pretty much, or that's what's going on in the background of it. So if you watch this, when I put L, see, it still comes up with the result. If I change this back to just A times B and put L, it should also say -0.8 or -8. Let's see. There it is, -8. So what's going on in the background is, whenever I put the times symbol, it's running that mul, that underscore, mul, underscore. And it's taking in self.data, which is the A, because it's doing A first, and so it's working on it itself. And then it's taking other, which is whatever you're multiplying it by. And then it does whatever operation you put in here. So you could technically put a plus symbol in here. This will look really weird, but okay, so it says A times B. All right, so I'll just copy this, put it down here. Or I'll put it down here rather. Okay, so originally, if you have A times B, it will do this, -6. But if I change that to a plus and run that, then go to here, it's actually going to add A and B together, even though I'm using the multiplication symbol. So that's really cool and unusual. Okay, ready? So this, before it said 2 times -3, which is -6, but now it's going to say 2 plus -3, which is the same as 2 minus 3, which is -1. So if I run it, A, what it says is times B, but it's actually plus, is -1. So I thought that was pretty cool. All right, now change this back so it's not confusing. Run it. Okay. So now this add and the multiply, they're doing the same types of things. It's just different operations. So down here, whenever you use the plus symbol, it's actually using this and running whatever is inside here, which is add self.data to to other.data. Okay, so, and these labels are just labeling it so it can put on that graph later, like you saw at the beginning of the video. Now I'll show L again, which is -8, or the value object of -8. So now I will go down here and run this. This is the thing for graphing stuff that Andrej wrote out. And I'll uncomment this and draw the graph. And there it is, like you saw from earlier. And we're going to go in and fill in these gradients. So as you can see, all of them are zeroed out right now. And this is remember A was -2, B is -3. When you do 2 times -3, that's -6, which comes over to here. And this is the C that was added to it. So there's the plus node. See, that was the times node for those A and B. And so you have E plus C. There's the plus. E plus C. And that's -6 plus 10 is +4. So then you add F to it. That's one of the things up there earlier, 2. F is -2. So this is a time symbol. So you have 4 times -2 is -8. And there's -8. So we want to back prop through here and find the gradients so that it can learn eventually. This video doesn't go into the actual learning part, or where it actually learns, but this will calculate the gradients, show how to do that so it can learn. Alright, so now if you look here, yes, so this is just a local thing showing another example. This is something that Andrej showed as well, and it's the y2 minus y1 over x2 minus x1 simplified to show the derivative. And okay, so now let's manually back prop through here. Say first of all, what is L with respect to L? So if I barely increase L by 0.0001 or something like that, then how many times that does the end result change? Well, it does it by 1 time that amount. So L dot grad is equal to 1. See, capital L. So L dot grad is equal to 1. And so if I run this and go over to here, now it shows the gradient is 1. So now we'll say, what is the derivative of L with respect to F? Okay, so if I barely bump up F, it'll change. Remember the multiplication derivative from earlier? I think it was the A times B. So the derivative of A was B because it's multiplying that H, that slight change, by that. So in this case, it's a multiply. So if you barely bump up F by H, then how many times does the end result of this local derivative change? The L with respect to F, a slight increase in F. So the amount it changes, since we're doing a multiply, is by 4 times that amount. So the derivative of the derivative of L with respect to F is D, which is 4. So derivative F is 4. So do F dot grad is equal to 4. Okay, now plot it, and this should show 4. Scoot it over so you can see it. And yep, there it is, 4. F is 4, the grad is. Okay, now same thing with D. So the gradient of D with respect, or gradient of L with respect to D is whatever F is, which is -2. So D dot grad equals -2. So do D dot grad equals -2. Run that, then redraw the graph, then scroll over, and D's gradient is -2. Alright, now let's back prop some more. Oh, sorry, one thing I forgot is this is the local derivative, each of these. It's just it's the gradient of this. But you multiply it with a previous global gradient, which in this case is 1. And so that comes out to be what it is right here, because if you multiply anything by 1, it's just that thing. Alright, so now if we back prop through here, this plus node, like when you do the derivative of plus, it's just 1 times, or it's just 1. Okay, so now what we do is say, or we would say, the derivative of this is 1 of E, and the derivative of C is 1. But that's the local derivatives. So remember, we multiply by the global derivative up to this point so far. So we have negative 2 times 1 is negative 2. So negative 2 would be the derivative of E and of C, since it's passing through a plus node. So derivative of D with respect to E and derivative of D with respect to C. So they are each of those locals is 1 times the global, and that would be negative 2 and negative 2. So E dot grad and C dot grad are both negative 2. So E dot grad equals negative 2, whoops, and C dot grad equals negative 2. Alrighty, so we'll now run this and this and check it, scroll over, and there's a negative 2 for E and C. Alright, now here's another times node. So as you can see, well, back here real quick, this doesn't connect to anything, so you don't keep following that through the graph, the computation graph. But this does connect, so you keep following it. So, the global is negative 2 so far, global derivative. Okay, so this is a times node. So do the local derivative first, then we can multiply by the global derivative. So whatever each of these answers are for the local derivatives, we would multiply those by negative 2, the global derivative so far. All right, so since it's a times node, the derivative of E with respect to A is B, following the same pattern. And B is negative 3. But now you multiply it by the global derivative of negative 2. So negative 3 times negative 2 is positive 6. So A dot grad is positive 6. A dot grad equals 6. A dot grad is 6. And last but not least is B. So B's local gradient is derivative of E with respect to B is equal to A, which is 2. So now you have the 2, and you have the global gradient of negative 2. So 2 times negative 2 is negative 4. So the gradient of E with respect to B is negative 4. So B dot grad is negative 4. B dot grad is equal to negative 4. Okay, if I run it, and there it is. Okay, so as you can see from Andrej's video, the grad of L is 1, the grad of D is negative 2, and F is 4. So, let's see, go back here. So L is 1. That's the graph that we made. D is negative 2, and F is 4. Okay. So if you go to the other part of it, zoom in so you can see it better. He shows that E grad is negative 2, and C's grad is negative 2. So that's what we came up with also. E's grad negative 2 and C grad negative 2. And finally, A6, B negative 4. So grad of A is 6 and grad of B is negative 4. So we got it right. Going over a summary real quick. Alright, so what we did was we imported the modules, saw what a function is, and input numbers, show how it calculated, plotted a graph to indicate what the slope is, then showed a bit of what a derivative is and a bit more intuition about it again, then created the value object and made the add and multiply, and at one point made it so we could change the multiply to add. Then ran the graph viz. This is what Andrej created, that part, and a lot of the parts. Then we used the computation graph, and we somewhat intuitively backpropagated through it, calculating the local derivatives and multiplying by the global derivative. And we set the derivatives to this, or the gradients to this, and displayed them on this graph with the nodes and edges. And so that is how you backpropagate through an artificial intelligence neural network. So what you would do is take the derivative of, if this was a weights in the neural network, just say if A was the weights and B was the input. So you would take the derivative of the loss, which is L, or the last thing, with respect to A. So if I barely change A, then how does that change the end result? How many times that changes does the end result change? So what you do is say, in order to train the neural net, you say A equals A minus a percentage of the gradient of L with respect to A. And what that'll do is it'll keep bumping. I'll show it on the graph real quick. What what it'll do, just say if it was right here, it'll keep bumping it. Since you did minus the gradient, it'll keep bumping that in the direction so that it gets closer and closer to here. And if it happens to jump over, it rocks back the other way. So it keeps doing that over and over and over until it gets closer and closer to the bottom. Vertical axis is the loss, and the horizontal axis is the weights, or the A in this case. So it'll keep bumping A until the slope is flat, which would be at the bottom of this shape. If you have any questions, just let me know. I'll leave a link in the video to Andrej's video, and hope you enjoyed it and hope you learned something. Thanks for watching. Hit that like and subscribe button so that YouTube knows that you want to see more videos, and so that it recommends it more to others. Hope you enjoy. Thanks.